Thanks, everyone, for coming out this evening. It's nice to see so many faces here, and actually quite a few familiar faces, former students from Edinburgh and other colleagues from industry. It's always an honor, of course, to be invited to speak at the ISTRAC-D. And before I begin, I just want to note two debts of gratitude that I owe to Dr. Angus Law, who works with me at the University of Edinburgh, who actually gave the previous talk in this series, and Dr. Danny Hopkin, who works at a company called OFR. And both of them have helped me to struggle through my thinking on what is actually a very difficult topic for me to talk about. I think it's actually quite a difficult topic for anyone to talk about. So this is the advert for my talk. I've pulled this from the ISTRAC-D website. And it says, Luke Bisby discusses fire resistance design, how chartered structural engineers can be confident that they've discharged their professional duties when designing structures for fire, and how they can assess whether their approach is appropriate. Now, that's quite a lot for me to actually do, hopefully in under an hour. I'm going to try to do all three of those things. And I honestly can't remember if I wrote this myself, what appears on the website, but I'm going to try to do justice to it. I went back and looked at it earlier in the week and thought, ooh, is that what I said I would do? So fundamentally, this talk is about trying to answer the question of what is adequate with regards to structural fire engineering. And my intent is to be a bit provocative and to open up some discussions that I think are actually very important for the structural engineering profession to have, particularly now in the United Kingdom. There have been two previous lectures in this series specifically focused on structural fire engineering. The first was by Mark O'Connor, whose title was Structural Engineering. To paraphrase what I took to be the key messages from Mark's talk, and apologies if I get this wrong in his opinion, he said the standard temperature time curve is not representative of real compartment fires. He said real structural response to fire is far more complicated than can be reproduced by a standard fire resistance test. And I'm going to come back to these ideas as I go through. And then he said if structural fire engineers embrace these ideas, they can reduce the amount of fire protection to structural steelwork and they can save money. But he also said that also can give us greater confidence that we've met the requirements of the building regulations. And of course, I agree with all of those statements. Angus Law, who, as I've said, is my colleague at the University of Edinburgh, the title of his talk was We Need to Talk About Timber. And Angus said, again, this is me paraphrasing Angus, the fire resistance design framework probably doesn't apply to uncommon building situations involving mass timber. And this is mostly because the fire you get in one of these buildings is too different from the fire which is implicitly assumed by the existing fire resistance framework. Okay, so there is an assumed and implicit fire that we use to design as structural designers. And as I said, I put these up because I'm going to come back to all of these ideas as I go through. Now, I'm going to say some things in this talk that are challenging to this institution and to its members. I'm going to ask chartered structural engineers to reflect on their ethical and legal obligations. I'm doing this because I, too, am a chartered structural engineer, because I wear an iron ring on the pinky finger of my working hand, and some of you will know what that means. And because of my own very challenging professional context, during the past 2.5 years. So as a chartered structural engineer, I am, of course, bound by the ISTRAC-D Code of Professional Conduct. And it says that I should subscribe to the Statement of Ethical Principles of the Engineering Profession, which is issued by the Engineering Council and the Royal Academy of Engineering. Although I have to say, one wonders if the word must should be there rather than the word should with respect to the context. Nonetheless, the Statement of Ethical Principles requires me as a chartered structural engineer to hold paramount the health and safety of others and to draw attention to hazards. And that's what I'm trying to do this evening. And to identify, evaluate, quantify, mitigate, and manage risks and not knowingly mislead or allow others to be misled. And so I'm going to try to lead you away from being misled, if that makes any sense. So I hope you'll permit me some self-indulgent, but I promise you relevant background. 20 years ago last month, this picture was taken. This is a picture of me starting my PhD. And my PhD was looking at the fire resistance of concrete columns, reinforced concrete columns, that had been strengthened by confining them with carbon fiber reinforced polymers. So there I am. I've built a reinforced concrete column. I'm wrapping it in carbon fiber. This carbon fiber is bonded with an epoxy, so it burns rather enthusiastically, it has to be said. And I was charged with working with an industrial partner to better understand the fire resistance of these types of structural elements so that they could actually be implemented in buildings. So we built some columns, we wrapped them in carbon fiber, we applied some insulation to them, we stuck them inside a fire testing furnace at the National Research Council of Canada in Ottawa. We subjected them to a vertical load that we decided was approximately the load that the column might be subjected to in a strengthened situation in service in a building. We closed those doors on the front, and we subjected that column to the standard fire, which is a standard temperature time curve, by using a bunch of very high-powered propane burners. We didn't know what the inadvertent eccentricity at the top of the column was. We didn't know what the fixity of the column was at the top or at the bottom. We couldn't measure its lateral deformation during the fire. We just put some load on it and we heated it until it broke, and we called that the fire resistance. We did all that because our industry sponsor for the project was focused on one thing and one thing only. He wanted to get a fire resistance rating. And yet the fire resistance justification that we came up with didn't need to be supported by full-scale fire resistance test. It didn't need to be supported by the detailed finite difference heat transfer models that I developed as part of my PhD. It didn't need to be supported by the detailed fiber section structural response models that I developed as part of my PhD. All that was needed was a little bit of fundamental understanding, a little bit of understanding of what fire resistance is, and a little bit of engineering judgment. But nonetheless, our industry partner got his 3-hour fire resistance rating, he got his certificate, and he went off into the world and made shed loads of money, I can tell you. And of course, I got my PhD, because here I am. But I knew that I hadn't earned it. And so I started my atonement, the making of amends for the sins of my PhD. And I was inspired in my atonement by the post-Cardington performance-based structural fire engineering design movement that was happening here in the UK at the time. See Mark O'Connor's prior talk if you want to learn more about Cardington and what came out of Cardington and what then happened in the industry as a consequence. I moved to the University of Edinburgh to become an evangelist structural fire engineer. I started spreading the gospel of performance-based structural fire engineering design. And this gospel was very well summarized by Mark O'Connor in the talk that he gave previously. And here I'm quoting directly from his conclusions without his permission, so apologies to Mark. He said, performance-based design, performance-based structural design for fire can lead to more economical design compared to simple approaches, so we can save money. It's suitable for more innovative and more complex buildings. I agree. It provides a better understanding of the actual structural behavior of the building during a possible fire. Again, I agree. And it can identify more critical parts of the structure for fire. And for more than a decade, I've been repeating these very same messages over and over and over. And I did and I do believe all of this. But in most cases, what I've found in talking to people is that the real justification for doing this work seems to be the financial savings. The financial savings that developers could reap as a consequence. And I started to wonder, surely, if we're genuinely trying to fulfill the requirements of the building regulations, shouldn't we be doing all of these other things anyway? And so then I started to feel delinquent. Was I, in fact, failing in my duties as a chartered structural engineer? And then one morning in the summer of 2017, I woke up very early in a hotel room in Sweden with my phone buzzing and beeping, and the world had changed forever. And I started to think much, much more deeply about our responsibilities as chartered structural engineers. And in particular, I started to think about this most important word, adequacy. What is adequate? Now, the first place most of us would normally look for guidance on this issue is in the building regulations. So I'm quoting from the building regulations, England and Wales. What do they say about the structural engineer's responsibilities with regards to fire safety? Well, in Part B, And here I'm cutting and pasting bits of the building regulations with apologies. Under Part B, amongst other things, it says, with respect to internal fire spread brackets structure, the building shall be designed and constructed so that in the event of a fire, its stability will be maintained for a reasonable period. Stability. What do we mean? What does it mean for something to be stable? Or perhaps more importantly, what does it mean for something to be unstable? How unstable? How much of the structure? Where? When? For how long? Reasonable period. What period of stability maintenance is reasonable in the event of a fire? These questions require engineering judgment. We don't have answers to these questions. So Part B says these things, and I'm going to talk in a minute about how we actually deliver on that requirement in the building regulations by using the approved documents. But we also need to look at Part A. Part A, structure. If you're a chartered structural engineer, this is the part you should be looking at most closely, I would imagine. And under A3, under disproportionate collapse, it says the building shall be constructed so that in the event of an accident, the building will not suffer collapse to an extent disproportionate to the cause. The use of the word accident is important. I've looked through all of the relevant guidance, both the UK guidance and the European guidance, and fire is absolutely caught under the term accident. So that includes fire. The building will not suffer collapse to an extent disproportionate to the cause. How much collapse is disproportionate to a fire occurring in the building? Again, engineering judgment is required in order to assess how much collapse is disproportionate to the cause of a fire in a building. So let's look a bit more deeply at this. So most of us in England would then go to the approved documents for guidance on how to meet the requirements of the building regulations. In terms of fire, we would end up in approved document B, as I've already mentioned. This is bits cut and paste from the latest version of approved document B. We'd find ourselves in section 7, load-bearing elements of structures, and we'd look and we'd find a section entitled Fire Resistance Standard. Fire resistance are very important, is a very important pair of words for us. And what it says is that the elements of structural frames, beams, columns, load-bearing walls, internal and external, should have, as a minimum, the fire resistance, again, there are those words, given in Appendix B, Table B3. So what does Table B3 tell us? Well, Table B3 actually points us almost immediately to Table B4 in the latest version of ADB. And this is the minimum periods of fire resistance. So what is this fire resistance, and what would it be for a building? So let's just hold up one potential building. Let's say I have a residential building. Let's say this building is a block of flats. Let's say this building is more than 30 meters tall or 15 stories. The reason I've chosen that should become obvious in a second. It's not a particularly uncommon building, though. A 15-story resi building in London is not that uncommon. If it's that tall, I must have sprinklers. So my building is sprinklered because I'm not allowed not to have sprinklers if it's a new build. And my fire resistance requirement would be 120 minutes. What does that mean? 120 minutes of fire resistance. I don't think that most structural engineers actually know. And I can say that because I was educated as a structural engineer at one of the best engineering schools in Canada, and I didn't know. I didn't know when I started my PhD. I'm not sure I knew when I finished my PhD. I'll come back to that in a minute. What does approved document A tell us about these accidents that we have to consider? Well, approved document A, if we look in there, we'll end up in section 5, reducing the sensitivity of the building to disproportionate collapse in the event of an accident. And again, accidents include fires. Definitely, there's no debate about that. What approved document A does is it talks about, in the context of disproportionate collapse, is it talks about consequence classes of buildings. And it has consequence classes 1, 2A, 2B, and 3. For consequence class 3, it says that a systematic risk assessment of the building should be undertaken, taking into account all the normal hazards that may reasonably be foreseen, together with any abnormal hazards. That's pretty clear about what we need to do. Systematic risk assessment. So what is a consequence class 3 building? And what would constitute a systematic risk assessment? And what hazards are we worried about? Let's think about fire. So if you want to know what the consequence classes are, you end up looking at Table 11. I recognize that many of you are unlikely to be able to see this, so I'll read it. Consequence class 3 buildings are down here at the bottom of the table. And it says, just as an example, all buildings defined above as consequence class 2A and 2B that exceed the limits on area or number of stories. So I go up and I look at 2B, and let's look at the first line of that. Hotels, blocks of flats, which is the building I looked at in approved document B, table B4, and other residential buildings greater than 4 stories but not exceeding 15 stories, or about, well, more than 30 meters actually, but 15 stories. Also included there, educational buildings greater than 1 story but not exceeding 15 stories, retail premises, offices greater than 4 stories but not exceeding 15 stories. So any building that's more than 15 stories, you are required to do this systematic risk assessment of the building, taking into account the hazards that may reasonably be foreseen. And there it is for us again. And I'm going to come back to both of these points in a minute in terms of how a fire engineer and a structural engineer might approach these two requirements in the building regulations. Just as a final point, it's worth always pointing out, I think, when we talk about the building regulations with respect to fire safety, and I think it's worth structural engineers and fire engineers pointing out to their clients, and perhaps more importantly to their clients' insurers, that the purpose of the building regulations is to secure reasonable standards of health and safety. It's not to protect the property, it's not to protect the business, it's not to protect the assets, it's to protect health and safety of persons. And so if you want more than that, that's a conversation that everybody should be having. I'm not sure that many people out there in the industry really have recognized that in a very fundamental way, and I think it's worth saying it as often as possible. So what is fire resistance? Fire resistance came up a lot there. What is fire resistance and where did it come from? This is something that I think all structural engineers should know, and so I'm going to labor the point, I'm afraid. And if you do know where fire resistance comes from, you know the history of it and the intent of it, then I'm sorry. This will be quite boring for you. I think it's super interesting, personally. So fire resistance is stated here. R or E or I, load-bearing capacity, capacity to insulate, and the capacity to prevent the spread of fire, have to be greater than or equal to some number of minutes. That's the 120 minutes from table B4. That's the fire resistance requirement. Okay. So then the natural question is, how would I assess R and E and I for a structure? If I go back and look at my table B4, the fundamental question here is, what does this 120 minutes actually mean? Where did it come from? Who decided? When? And using what knowledge? Right? These are the questions we need to ask. So what's the fire I need to provide resistance against? Given that all fires are different, as we know. These are some of the earliest available photos of what we might call modern, in quotes, fire resistance tests on structural elements. These were done by Edwin Sachs here in London, just up the road actually, in Regent's Park, in 1902, 1903. And these consisted of brick huts. You can see on the left there, it's that little sign in the top left corner says hut number 1. The other one is hut number 2. With fuel supply provided, and again you can see the fuel supply in the image there. In this case, structural elements were placed on top of the huts and were loaded, as you can see there, with a pile of what looked like bricks. And the elements were heated until they failed. And this, Sachs and colleagues were trying to get the structural elements as hot as possible, as fast as possible, and for as long as possible. And here's what they achieved on one particular day. It looks like August 12th, 1903, just past tea time, given that the time axis starts at 4 p.m. and goes in 15-minute intervals. And more than a decade later, this is just one test, more than a decade later, international meetings were actually held to try to decide with British and American colleagues what the standard fire, or what a standard fire, should be. And by committee, these points were chosen. And I think we can guess how they chose those points, although I've not seen a written record of how those points were chosen. And that led to this curve being defined by committee. And that eventually became the UK standard. And it also became the US standard. And eventually it also became the ISO standard. And it's still the standard that we use today. At the time, Ira Wolfson, who was the American chap who was leading this effort, he made this incredibly prescient statement. He said, "We want to get it as nearly right as possible before it is finally adopted, because after it is adopted by these various organizations, it will be pretty hard to change." Also demonstrating that he was a true master in the art of understatement. So where does fire resistance come from, and what fire am I providing resistance against? It was ad hoc tests that looked something like this. This is one of Wilson's tests in the US from the same era. That led to a standard fire resistance time temperature curve that looked not something like, exactly like this. And I don't know if you noticed in the previous plot, but it ended at 1 hour and 45 minutes. So it appears what they did is just straight-lined it from that point. And that remains almost exactly what we use today. So if I was running a fire resistance test today, I'd be using a very fancy version of the brick-lined box on the left. And there's some really important things to understand about this. Really important things to understand. Standard fire resistance tests, standard fire tests were originally conceived as comparative tests of alleged fireproof building systems. These tests were being used to compare systems, not to rate systems. The standard fire curve came into existence in a world where fire resistance ratings did not yet exist. The standard fire is not a realistic representation of a building fire in a number of respects. It was set out by committee, as I've mentioned, before anyone had actually bothered to measure the temperatures in a real building fire. They hadn't yet done the research. And it was originally suggested without the intent to assign any fire resistance ratings, as I've mentioned. But this standard fire bears little resemblance to the fire that I'm going to get in my actual building. So how can I relate the one to the other, the standard fire to the actual fire? Well, in the 1920s, a chap called Simon Ingberg started doing tests of fires in actual compartments with actual fuel and measuring the response. And this is a schematic, a cartoonish diagram to show the kinds of response that he was observing. He noticed that fires grow and burn and then run out of fuel and cool. And he wanted to relate this fire, the actual fire, to the standard fire, because the standard fire had been set in stone 5 to 10 years earlier. So what did he do? He said, okay, well, if I have a standard fire and I have a natural fire, what area above a threshold temperature under the natural fire would be captured by the same duration of heating under the standard fire? So he said, if these two areas are equal, that is an equivalent fire. And that is why fire resistance has units of time. So Simon Ingberg postulated that the full history, i.e. until burnout of the fuel, until we've run out of fuel and the fire has gone away without any intervention, of a compartment fire can be related to the duration of the standard fire that gives the same area under the curve, and he called this fire severity. It should actually have units of Kelvin time rather than time, if you want to be specific about what it is. Just to prove that I'm not making this all up with my cartoon, here's some of Ingberg's original data. You can see the standard fire curve sort of slightly there, and you can see a number of cooling curves. So he didn't actually take a straight line. It's slightly more complicated, but that is essentially what he did. And you can see an actual fire curve there. So I've agreed our standard fire. We've made that, and we've agreed the method to relate our standard fire to a real fire. But we've not yet figured out for a given building how much fire resistance we need. Do I need 30 minutes or 60 minutes or 90 minutes or 120 minutes? How much fire resistance do I need? And so Ingberg then did a whole bunch of compartment fire tests. And you can see here he's listing off 10 different tests of offices and record rooms in this case. You can see what they were furnished with. You can see what kind of floor they had. You can see if it was a small or a large building. And you can see, importantly, how much fuel in pounds per square foot, or converted to energy based on the heat of combustion of the materials, how much energy per unit floor area or per unit volume for those rooms was there, and then how much equivalent fire duration based on his equal area concept did he get. So he runs the fire, he calculates the equal area, and he gets the number. And you can see down the left hand of the pink shaded column there, you can see times, 1 hour, 3 minutes, 1 hour, 26 minutes, 1 hour, 5 minutes, based on those different fuel loads and compartment configurations. And based on all that work, Ingberg then proposed a scheme by which the fire resistance requirement for a building would be based on the amount of fuel that was in it. So if you have a room with 10 pounds per square feet in it, you need an hour of fire resistance. If you had 60, you need 7 hours and 30 minutes. So Ingberg, incorrectly, it has to be said, said that fire severity depends only on fuel load. Fire resistance requirements for different occupancies are explicitly linked to fuel loads, which are explicitly linked to burnout fires. And of course, Ingberg was wrong. We know much more about fire dynamics and fire science now. We know that this isn't true. We know that ventilation is important. We know that thermal boundary conditions are important. We know that various cross breezes and various other things are important. But what's important to take away from that is that fire resistance originally implied burnout without intervention. It implied that the fuel burns and goes away. It didn't imply that a fire resistance of 120 minutes means that if the building falls down at 121 minutes, we have done our job. And if you want evidence of this, I cannot recommend highly enough reading PWBS stands for the Post-War Building Studies. I would recommend anyone in the room with any interest, get yourself a copy of the Post-War Building Studies and read them. It's all laid out, plain as day, in the 1940s. Oh, and just as one final point here, Angus Law, in the previous talk in this series, pointed out that fire resistance shouldn't apply to CLT buildings with significant amounts of exposed timber surfaces, because those exposed timber surfaces will contribute to the fire dynamics in the compartment and extend the duration of burning. Ingberg recognized this in the 1920s. You can see in the bit that highlights just there, total combustible content inclusive of finished floors and trim. So if Ingberg had exposed CLT, he would have included it in the fuel load at the very least. And that's where fire resistance comes from. And it's also why it has units of time. But of course, this isn't real time. This is equivalent time. It has no specific relationship to real time. And I think that's actually a very serious problem in the discourse around these issues. And so anytime I'm asked to speak about this, I point out that we should actually change the way we're talking about it. I think we should say fire resistance points. And I think this would actually go a long way to stopping the inertia of this flawed concept. If we simply stop using minutes or hours and we start saying points, it's a 30-point column, it's a 60-point door. And that removes this false reliance on the idea of time. But enough about the fire. This is the I struck T, of course, and I'm meant to be talking about structures, so sorry about that. Most people who've looked seriously at the standard fire resistance tests in terms of the structural mechanics aspects, so forget the heating curve, let's talk about the structural mechanics of a fire resistance test. Most people who've looked at it for more than half a century have reached approximately the same conclusion. Fire resistance tests fail to capture or predict real structural response to fire. On the left, I have a burning building. That's I think, 46-story steel-framed office building in New York City that was subjected to an office contents fire and collapsed entirely. That building is made up of a very complicated three-dimensional system of beams and columns and slabs, composite, various interesting types of connections, all sorts of interesting geometries and interactions in that building when it's being heated. The way that that building would be conceptualized via fire resistance testing, which is how we achieve or understand fire resistance, would be that we would build a box. We would put some propane burners in the walls of that box. We would put our structural element, whether it's a beam or a slab, we would isolate it on top of that box. We would put some load on it that represents the in-service loading that we would expect at the time of a fire. And we would turn on our propane so that it follows the fire resistance curve that I showed you previously, which represents the committee decision from the early 1900s, as I've already said. And we would then wait. And we would wait for that structural element to collapse and fall into the furnace, or we would wait, if this was a slab or a wall, or a door for that matter, we would wait for either hot gases to pass through that structural element, or we would wait for the temperature on the unexposed surface of that element to exceed some upper temperature limit, which incidentally, as far as I can tell, represents the auto-ignition temperature of industrial cotton waste continuously in contact with the outer surface. So again, it's worth asking ourselves, does this sound like part of a systematic risk assessment that is demanded in approved document A? And indeed, does use of the standard fire sound like part of a systematic risk assessment that is demanded of structural engineers in approved document A? Well, NIST, the National Institute of Standards and Technology in the US, after spending 7 years investigating the collapses of the World Trade Center towers 1, 2, and 7, which incidentally is the building on the left in my picture here, they said no, it doesn't. Thermal expansion effects can cause collapse and are not explicitly considered in design practice for fire resistance. And they were pretty categorical about that, and they issued a number of recommendations on that basis. A little bit closer to home, and by home I mean Canada, Harmathi and Lee, who were two seminal figures in the fire research community in the 1970s in Canada, said this about fire resistance and fire resistance testing. In a strict sense, the standard fire resistance is not a measure of the actual performance of an element in a fire and is not even a perfect measure for comparison. The fire load concept must be abandoned, and we have to come up with a truer representation of the conditions that will probably be met. This is 4 years before I was born. Here in the UK, in 1981, Margaret Law, who's probably the seminal figure in UK fire safety engineering, said the standard temperature time curve is not representative of fire in a real building. Indeed, she was even more harsh. Indeed, it is physically unrealistic and contradicts available knowledge. The required duration of fire exposure in the standard test is open to criticism on a number of grounds and should be revisited. Has not yet been seriously revisited. The loading and end conditions in the standard test are not well defined and clearly cannot represent the continuity, restraint, redistribution, and membrane action in real buildings. And Margaret Law wasn't even a structural engineer, and she could recognize this about our structural response modeling in furnace tests. So at this point, when I give talks like this, someone normally says, but Luke, why aren't buildings falling down in fires then, if this is also wrong or also irrational? It's not actually true. They sometimes do, either partially or totally, just not very often. But I would go so far as to say that every time a structure is seriously challenged by a fire, every time a fire gets out of control in a structure, which is what we're meant to be designing for, the structure responds in a way that would have been very difficult or impossible to predict beforehand. And that's true for me also, someone who gets involved in a lot of fire investigations of fires in real buildings. And even if we assume that these failures that I'm putting up here, partway through the fire, it has to be said, even if we assume that they can all be discounted for a host of different reasons, the sprinklers weren't working properly, the building was under construction, the firefighters didn't intervene, we still have to ask the question if that's because we've actually undertaken a systematic risk assessment, or simply because we're lucky, or maybe because we're just very, very conservative in the way that we design buildings to resist fire, or maybe both in some combination. So what would be better? How should we change? How should the structural engineering profession change? What new guidance is required? Well, to be honest, I've looked, and I think it's already there in the codes. It's just really hard to do. And so in most cases, it's not happening. To give you an example of it being in the codes, in the US since 2010, and actually as a consequence of the 9/11 attacks and the collapses that were observed in 9/11, the load case for extraordinary events, as they call them, which includes fire, has included a new term, AK. This AK term represents the load or load effects resulting from the extraordinary event itself. So in the case of fire, this would require designers to account, for example, for self-stressing due to differential thermal expansion on heating, or lateral push out of columns when a floor plate expands in a building in a fire. In the UK, if we follow the approved document B route to meet the requirements of B3 that I put up earlier, we would eventually find our way to the Eurocodes, where the combination of actions for accidental design situations, again, which includes fire, is given here in a horrendously opaque format, it has to be said. So you'll have to take my word for it, unless you know the Eurocodes inside out, that this term here, this AD, is essentially the same as the AK term in the ASCE equation that I put up previously. And actually, maybe I'll just go back to that ASCE equation here, because structural engineers like this equation because it's pretty obvious. Dead load, live load, snow load, they tend to be less than 1 because it's an accidental load case, and my AK term has been added to account for the fire. Eurocode does essentially the same thing. It has this term AD, and you can see here that AD represents the design value of the indirect effects of the thermal actions due to fire. So what are these indirect effects, these design actions of the indirect effects, and how would we calculate them? Well, the Eurocode gives us guidance on this in Section 4 of 1991, Part 1, Part 2, I think, where it's talking about the mechanical actions that you should consider for structural analysis. And it says, for assessment of the indirect actions, the following should be considered. Constrained thermal expansion of the members, differing thermal expansion within statically indeterminate members, thermal gradients within cross-sections giving internal stresses, thermal expansion of adjacent members, e.g. displacement of column head due to expanding floor slab, as I just mentioned, thermal expansion of members affecting other members outside of the fire compartment. So it's giving us a lot of guidance about what we, as chartered structural engineers, need to do to consider these indirect actions AD. So who's calculating this for Category 3 buildings as part of a systematic risk assessment in the United Kingdom? Who is calculating AD in our case? I don't know. Has anyone in this room ever calculated AD? I've never seen it done. Now in the UK, the question is why have I never seen it done? Now in the UK, this might be because the Eurocodes do appear to give us a free pass. Right at the end of the page that I put up previously, they have this clause 4 that I've just highlighted and expanded here. And it says that indirect actions from adjacent members need not be considered when fire safety requirements refer to members under standard fire conditions. So if you're just giving 120 minutes fire resistance, you can actually just use your furnace test result, is what this seems to say. And that's great for the fire engineer because it's approved document B that sends us looking here for guidance, not approved document A. Approved document B doesn't require a systematic risk assessment. It only requires that we provide fire resistance. Unfortunately, for chartered structural engineers like me and many of you, approved document A does. So if I step back and look at this, here's the process for a fire safety engineer under Part B of the building regulations. They'll go to Part B, they'll read Clause B3, they will then most likely go and look at the approved document B. That'll lead them to Table B4. They'll find their 120-minute fire resistance. How do I provide 120-minute fire resistance? I'll go to the Eurocodes. The Eurocodes tell me that I can just use the simplified methods that are based on furnace tests, and I'm happy. I can point at that method for having met my obligations. The structural engineer, unfortunately, and actually, it would be unreasonable at this stage to expect a fire safety engineer to undertake a systematic risk assessment for disproportionate collapse caused by fire, which is demanded by approved document A, because the fire safety engineer is clearly not competent to do that. That's clearly the role of the structural engineer. So the structural engineer, in looking at Part A, will go to Part A3 that I've put up previously. They will then go to approved document A. They will look at the consequence classes. For consequence class 3, they'll find that they need to undertake a systematic risk assessment. They'll then go look in the Eurocodes. Unless they decide that simply providing 120 minutes fire resistance does constitute a systematic risk assessment, taking into account all of the hazards that might be expected, which would be the prerogative of the structural engineer, despite the fact that it's clear that I don't necessarily think that's an appropriate thing to do in many cases. How do they calculate AD? This actually, I think, puts chartered structural engineers in a very difficult position, and I'm surprised that it hasn't come up before. So unless I'm comfortable, like I said, that providing 120 minutes fire resistance constitutes a systematic risk assessment, I need to do something that's more technically defensible. If something goes wrong, what am I going to point at? Of course, I'd love to be told that this is what's happening out there in the real world, that people are routinely undertaking systematic structural risk assessments for fire, and that they're routinely calculating AD or some equivalent means of undertaking a systematic risk assessment. But I haven't seen it happen, and I don't know if it's happening. And so that brings me back to luck or large conservatisms. Why aren't we seeing structures lose stability in fires more often? Is it because there aren't a lot of fires that challenge structures, which is essentially lucky? Or is it because our structures are so over-designed for fire that we can treat it in this semi-irrational way and we never witness the failures? Because there's so much extra strength in them. I honestly don't know. For a given building, I honestly don't know. And I think it depends very much on the building. And I think we have to look at each building specifically in order to have any sense of what the answer to that question is. But I do wonder if structural engineers ought to spend a bit more time and effort asking themselves this question. So delivering adequacy. How do we deliver adequacy? This was the thing I promised that I would help you to try to do as chartered structural engineers. In accordance with our Code of Professional Conduct and in accordance with the Statement of Ethical Principles and in accordance with the requirements of the building regulations and the associated statutory guidance, I think we need to start treating fire as a structural design load, genuinely. This is a very, very hard thing to do. It's not easy to do this work. But I think it's what we have to do as a profession. And so after more than a decade of spreading the structural fire engineering gospel, I find myself as a structural engineer and a fellow of the Institution of Fire Engineers and someone who came to the UK to become a structural fire engineer. I find myself in an interesting position. I find myself wishing myself into non-existence. Because I don't think structural fire engineering is actually a thing. I think it's just structural engineering. And I think it's therefore the responsibility and the realm of this institution and of the members of this institution. Thanks for listening.